Hello, today I'm going over atomic number, mass number, and isotopes lecture. So this is a introduction to these three concepts. And we've been talking about structure of the atom, so this is going to take us a little bit further and help us to understand how elements are arranged on the periodic table. Every atom belongs to a specific element, and scientists use the atomic number to identify it. So atomic number is usually going to be at the top of this box for a specific element. Carbon here is 6. The atomic number tells us how many protons are in the nucleus of an atom. Every carbon atom has 6 protons. Okay, so this is atomic number, tells us how many protons. All carbons have 6. For example, every carbon atom has an atomic number of 6 because it always contains 6 protons. This number is unique to each element, acting like a fingerprint for identification. So if you know how many protons an element has, you know what element that is. The atomic number also determines the number of electrons in a neutral atom. So the number of electrons is always going to be balancing the number of protons. They'll be equal in a neutral atom. Now, we can change the number of electrons, but we are not getting to that right now. In a normal neutral atom, they'll be equal to each other. Since electrons have a negative charge, they balance the positive charge of the protons. This balance affects how atoms interact and form chemical bonds with other atoms. So what we see is that when one atom bonds with another or links up with another, that's going to be from their electrons, based on how many electrons they have, if they're missing any, if they have extra. That's going to determine what kind of chemical bonds form. Understanding the atomic number helps explain why each element behaves differently in chemical reactions. Okay. Oh, and this one here, if you count up, we know that protons are in blue, and so you can count up how many of the protons there are, and that'll tell you what element this one is. 1, 2, 3, 4, 5, 6, 7, 8. And 8, I believe, is oxygen. Okay, the mass number. So we talked about atomic number, now we're talking about mass number. Mass number measures the total number of protons and neutrons in an atom's nucleus. For example, a carbon atom has 6 protons and 6 neutrons, has a mass number of 12. So here's our carbon, right? 1, 2, 3, 4, 5, 6. Yep, 6 protons, so we know it's carbon. But to get the mass number, I'm going to add those 6 carbons and 1, 2, 3, 4, 5, 6, 7, 8 neutrons here. When I put 6 and 8 together, that's going to give me 14. So this one actually has a mass of 14. A normal carbon would have a mass of 12, 6 and 6. The mass number gives scientists a way of compare the weight of atoms. It can vary for atoms of the same element because the number of neutrons can change. That's what we saw over here. We actually had more than 6 neutrons, which is certainly possible, but the number of protons does not change. Mass number is different from atomic number because it is not unique to each element. While the atomic number defines the element itself, the mass number reflects the specific combinations of protons and neutrons. This is important for understanding why some atoms are heavier or lighter than others. So if you take a look at these three, we've got sulfur, chlorine, argon. Now, in these abbreviations, this number at the top is the mass number. And you'll see that sulfur has a mass number here in this particular instance of 40. Chlorine has a mass number of 40, and the argon has a mass number of 40. It should be AR. So even though they're different elements, they have the same mass number, but they have a different atomic number. The atomic number for sulfur is 16, for chlorine 17, and for argon 18. Okay. Calculating the mass number is essential when studying atomic structure and isotopes. So we'll get into isotopes right now, which we've already discussed a little bit. Atoms of the same element that have different number of neutrons are called isotopes. So we saw an isotope back here. Normally carbon would have 6 protons, 6 neutrons. Well, this one had a different number, right? This one had 14 instead of 12. So this is actually an isotope of carbon. And you can look at these. These are all isotopes of carbon. Carbon 12, carbon 13, carbon 14. Same number of protons, different number of neutrons. For example, carbon 12 and carbon 14 are both carbon atoms. But carbon 14 has 2 extra neutrons. That's what we see here, 6 and 8. Isotopes have nearly identical chemical properties, but may differ in stability and mass. Definitely different in mass, right? Because we have different mass numbers, 12, 13, 14. This makes isotopes useful in a variety of scientific applications. So when we're dealing with isotopes, right, same element, different number of neutrons, some are stable and some are unstable. So that's what we're talking about here. And if it's unstable, it's going to be radioactive. Some isotopes are radioactive, meaning they decay over time and release energy, while others are stable. The reason that they decay is because they have to release this energy. They are unstable. If they're stable, they don't have to release any extra energy. They're fine. They'll stay the same. They'll stay how they are. If they're radioactive and decay, they're gonna change. Radioactive isotopes are used in medicine, such as cancer treatment or imaging, and in dating ancient artifacts. Stable isotopes are used in research, like tracking chemical reactions or studying climate changes. Down here, we see a uranium atom that is radioactive. It's unstable, and usually they're unstable because they have so many extra neutrons. That's what we find a lot. Having those extra neutrons up here makes them unstable, and they want to release some of their extra energy to become stable. And that's what this decay is. So this is, you're getting a decay. So part of it is breaking off so that it becomes more stable. And you can see that the mass also changed. Mass changed, and in this particular case, we're not going into nuclear decay right now, but in this particular case, the element also changed. All right, this should get us started at least. And if you have any questions, please let me know. Thanks.